Good afternoon, everybody. And as Chris alluded to, my talk today is going to focus on using seaweed aquaculture, and particularly sugar kelp, Saccharina latisma, to help mitigate one of the most challenging problems facing coastal waters today. And that's the problem of excessive nitrogen loading, which is fueling eutrophication in coastal waters around the world, driving dense phytoplankton blooms, losses of seagrasses due to light limitation, and death of animal life due to low oxygen. So this is a global water quality issue, particularly in areas of high human population, like Long Island, New York. And as you all know, at the western end of Long Island is New York City. It's the most densely populated city in the country with over 9 million people. And as you move east away from New York City and across Long Island, there's a general improvement in coastal water quality as population density declines. But across this entire water quality gradient, nitrogen pollution is a serious concern. So this is a map of water quality impairments around Long Island that's produced annually by the Gobler Lab. And it shows the location of various nitrogen-related problems like hypoxia, fish kills, and an array of harmful algal blooms. And as you can see, the problems are concentrated in small bays and harbors along the coast of Long Island, as well as in the western portion of Long Island Sound closest to New York City. So as pointed out in previous talks and shown in the animation here, the primary source of nitrogen to Long Island coastal waters is septic systems, with the nitrogen entering coastal waters through submarine groundwater discharge. And to address this problem, in 2020, Suffolk County, which covers 2/3 of Long Island, enacted the Suffolk County Subwatersheds Wastewater Plan. So this plan, it's a $4 billion plan, which we've heard a lot about today. It's a multi-phase plan for transitioning Long Island away from traditional cesspools and toward innovative and alternative on-site wastewater treatment systems that remove nitrogen. So this map shows the target regions for different phases of the plan, with the goal of upgrading 200,000 septic systems by the year 2050. So this is a long-term plan. And as Nils pointed out at the beginning of his talk, there's also legacy nitrogen that's in the groundwater that will be entering our coastal waters for a long time to come. So what can be done now to mitigate nitrogen pollution while these land-based solutions roll out? So one in-the-water solution garnering much attention is nutrient bioextraction through shellfish and seaweed aquaculture. What makes these two crops extractive is the fact that they're zero-input crops. They require no feeds or fertilizers. Rather than being fed, farm shellfish and seaweeds extract nutrition from the waters around them. In the case of shellfish, they assimilate nitrogen from the phytoplankton they feed on, while also releasing nitrogenous waste in biodeposits. Seaweeds, on the other hand, provide a more direct means of nitrogen removal in that they assimilate dissolved inorganic nitrogen directly from the surrounding water. And when seaweeds and shellfish are harvested, the nitrogen contained in their tissues is removed from the system. And it's this harvest component of nutrient bioextraction that I'll focus on here. So the goals of the study were to, one, quantify the amount of nitrogen that can be extracted through sugar kelp aquaculture across a range of water qualities and depths around Long Island, New York. And two, to compare nitrogen bioextraction of kelp to oyster farming and estimate the combined ecosystem services of an integrated kelp oyster farm. So to quantify nitrogen bioextraction, we conducted kelp cultivation experiments at 8 locations over 2 growing seasons in 2022 and 2023. The locations are shown with stars on this map, and they span the gradient in water quality across Long Island. From the heavily nitrogen-impacted waters in the East River at the western end of Long Island Sound, eastward to the cleaner waters of the Peconic Estuary, where we installed kelp on oyster farms. The eight locations also covered a range of water depths from deeper waters between 20 and 30 feet in the East River and the Peconic Estuary, to shallow nearshore areas in small suburban bays where low tide water depths were under 3 feet. So these 3 shallow bays included Mauritius Bay on the south shore and Northport and Mount Sinai harbors on the north shore. So we cultivated kelp along horizontal longlines at all sites with different methods of installation used for shallow and deep waters. For the deep water location shown with the red stars we used a conventional longline method for growing kelp, shown in the diagram here, where kelp is grown from a suspended horizontal line below the surface that extends between two moorings. For areas where mean low water depths are below 3 feet, I developed a staked line system in which kelp lines are staked a fixed distance above the bottom using screw anchors at each end. At each site, we installed 3 to 4 lines of kelp that were between 100 to 200 feet long. To monitor growth, we collected 3 kelp samples per line every month through the growing season, with each sample including all kelp biomass from a 15-centimeter length of line. We then brought these samples back to the lab for a suite of measurements, including wet and dry weights, blade lengths, and carbon and nitrogen content, which was run on a combustion elemental analyzer. So let's look at the results. Overall, we successfully grew kelp across all sites and water depths, but with large variation in kelp growth, as you can see in the pictures here. So the figures on the right plot the average line yields for each site in terms of kilograms of nitrogen per meter of line over the 2022 and 2023 growing seasons in the top and bottom figures. Now, as you can see on the x-axis, the growing season goes from December, when the lines are seeded, to May or June, when the kelp is harvested. The sites are color-coded in these plots, and their locations are shown with stars on the map on the left. For the 4 Peconic estuary sites, I'm only including data for one site for clarity of the graphs, and this was the site that had the highest growth among the 4 sites in the Peconic estuary. So, at all sites, peak biomass was reached in May to early June, followed by declines in biomass as the kelp began to deteriorate as waters warmed. Line yields at peak biomass ranged 40-fold among sites, from under 1 kilogram to nearly 17 kilograms of kelp per meter of line. And the differences among sites were consistent between the 2 years. So at peak biomass, I'm going to attempt to use the laser, but peak biomass, just basically shown right here, here. So at peak biomass, line yields were significantly higher in the East River and Mauritius Bay than all other sites, with the East River higher than Mauritius Bay in 2023. Mount Sinai and Northport had similar yields each year that exceeded that in the Peconic estuary, which had the lowest kelp growth. And here's just a couple pictures to give you a visual of the amount of biomass produced along single lines at the highest growth sites in the East River and Mauritius Bay. Now, when we compare the nitrogen content in the kelp tissue at peak biomass, we found a 3-fold range across sites in both years, from about 0.8 to 2.7% nitrogen in the kelp tissue. In each year, the highest nitrogen content was found in kelp tissue from the East River, where kelp growth was also highest. And in each year, we also saw declining nitrogen content in kelp tissue as you move east from New York City, with the exception of Mauritius Bay, where kelp growth was also very high. So using this data, let's now make some nitrogen bioextraction calculations. So first, I'll show nitrogen extraction in terms of nitrogen removed per meter of kelp line. And this was simply calculated as the dry kelp biomass per meter of line times the percent nitrogen in the kelp tissue. So across sites and years, nitrogen bioextraction ranged from 0.3 to just over 50 grams of nitrogen per meter of line. The highest nitrogen removal rates were in the East River, the most urban site, followed by Mauritius Bay, the shallowest site. And this was primarily due to the higher kelp growth rates at these sites, and to a smaller extent to the higher tissue nitrogen content. Nitrogen bioextraction was significantly lower at the other 3 sites and was virtually non-existent in the Peconic estuary, due to the very low kelp growth rates there and tissue nitrogen content. So to convert nitrogen removal from a per unit length basis to a per unit area basis, I assumed either 1.5 meter or 6 meter spacing between kelp lines. So these are the line spacings that we successfully used in this study, with 1.5 meter line spacing used in shallow waters, where you can get in the water and walk between lines, and 6 meter line spacing used in deeper waters where we needed to maneuver a boat between the lines. These are also the same line spacing used in previous bioextraction estimates by Kim et al. In 2015. And I also want to point out that a 1.5 meter line spacing is effectively being used at New York's first commercial kelp farm in Moriches Bay. So this is a real world estimate. So at 1.5 meter line spacing, approximately 6,700 linear meters of kelp line can be installed per hectare. And at 6 meter line spacing, 1,700 meters of line per hectare. And multiplying the linear meters of kelp line by the nitrogen extracted per meter, we calculate nitrogen removal rates ranging across sites from 1 to about 339 kilograms of nitrogen per hectare. Again, I'll just point out that the highest nitrogen removal rates were found in the East River, the most nitrogen impacted site, followed by Moriches Bay, a shallow suburban lagoon. So how do these nitrogen removal rates compare with that obtained through oyster aquaculture? So to estimate oyster bioextraction, I used measurements of total nitrogen per oyster from a study that I was a part of, and it's published in a 2015 paper. And in that study, we cultivated oysters in cages in 2 Long Island locations, Jamaica Bay and Great South Bay. And these 2 sites nicely paralleled the 2 sites where we found the best kelp growth, the East River and Moriches Bay. So both Jamaica Bay and the East River are urban water bodies heavily impacted by nitrogen, while the Great South Bay and Moriches Bay are shallow suburban lagoons with lower nitrogen loading on Long Island South Shore. So in this study, we found an average of 0.19 grams of nitrogen per oyster in Jamaica Bay and 0.11 grams of nitrogen in Great South Bay. And this difference was due to the faster growth rates of the Jamaica Bay oysters, which averaged 77 millimeters shell height at the end of the experiment, where Great South Bay was about 65 millimeters shell height at the end of the experiment. Now, the important thing I want to point out about this study also is that the cultivation period was only 5 months, okay? So that went from June to October. And this is the exact opposite growing season from kelp. So the kelp being farmed from December to about June, and the oysters being farmed from June to October. Almost all of this nitrogen contained per oyster was extracted during that growing period. So when they were put in as small seed, the amount of nitrogen in the oysters at that time was negligible. So all of that nitrogen per oyster was extracted during that 5-month period. So next, I assumed a harvest rate of about 1 million oysters per hectare per year. And this is a realistic rate. I owned an oyster farm for about 10 years, so this is a realistic rate at a very well-run oyster farm anyway. And it's also a value used in other papers, such as by Grizzle et al. For these nutrient bioextraction calculations. So multiplying the nitrogen contained per oyster by this annual harvest rate resulted in nitrogen bioextraction rates of 110 kilograms per hectare per year in Great South Bay and 190 kilograms per hectare per year in Jamaica Bay. So compared to kelp, nitrogen removal was 1.8 times greater through kelp than oyster aquaculture in both the urban waters around New York City and the suburban lagoons on Long Island South Shore, with both kelp and oysters having higher rates of nitrogen removal in the urban locations. Now, if we combine the 2 crops, with kelp grown from December through May and oysters from June through October, we estimate the combined annual nitrogen removal rate is 530 kilograms of nitrogen per hectare per year in urban waters and about 300 in the suburban lagoons. So to relate these numbers to the land-based nitrogen mitigation strategies we've been talking about a lot today, this range is equivalent nitrogen removal of between 56 to 97 cesspool upgrades on Long Island. And at an average cost of about $20,000 per upgrade, the combined nitrogen removal of a 1 hectare integrated kelp and oyster farm equates to about $1.12 to $1.94 million per year. And I also just want to point out that these ecosystem services provided by an integrated kelp oyster farm can be expanded even further with the addition of summer growing seaweeds like gracilaria or ulva. And that's been a focus of research in Chris's lab also over the past several years. So I'll just summarize this all up. We found large differences in kelp growth and tissue nitrogen content among locations that spanned a gradient in water quality across Long Island. And this resulted in large differences in nitrogen bioextraction rates among sites ranging from about 1 to 340 kilograms of nitrogen per year, with the highest rates found in the most nitrogen-impacted waters and the lowest rates in the cleaner waters of the Peconic Estuary. Compared to oyster farming, we estimate that kelp farming provides almost double the nitrogen removal rate on a per-area basis. And these results suggest that the integration of kelp into oyster farms can greatly enhance the ecosystem service of nitrogen removal, particularly in nitrogen-impacted waters most in need of remediation. And just want to, a few acknowledgements. All this work was done with a lot of help from everybody in Global Lab, referred to as the kelp heads in Chris's lab. I want to also thank collaborators. We've had a Green Wave and SUNY Maritime College on these projects. A lot of oyster farms. I'm just highlighting Great Gun Shellfish here, where we've been growing kelp for 6 years and done a lot of our initial work there and continue to do some great work there. And I've kind of combined data from several studies that have been funded by a number of organizations. So thank you.